Welcome to the Byte Code. I'm your Shafu. And I saw you tweeting this thing about OpenVM, which is this new zkVM that he has been working on with some other people. Thanks for taking the time, man.
Yeah, thanks for having me on again. I'm excited to jump in and talk a little bit about what we're releasing with OpenVM.
Awesome, man. Yeah, let's get into it. What is OpenVM?
Yeah, so OpenVM is a new zkVM framework, which really prioritizes modularity and extensibility. We've been developing this at Axiom in collaboration with Scroll and some other individual contributors for the last 6 or 9 months. We just had our first release in late December. With OpenVM, we're taking kind of a new approach to how zkVMs are constructed. And so what that means is we want to allow developers to customize a zkVM for their performance needs without really trading off on getting the best possible performance across all workloads.
Interesting. Okay, maybe let's start here. Let's talk about the current landscape. Like, what are we talking about? What do we have currently in terms of zkVMs?
Yeah. I think if we go back through the history of zkVMs, probably the first zkVM of prominence is Cairo, which is sort of a very zk tailored VM architecture with an instruction set that's kind of custom for zk to achieve, a good enough performance with the state of the technology at the time. After that, I think we saw some attempts to make similar zk tailored VMs. And then in around 2022, there was a wave of zk EVMs. So those were architected with very custom circuits to match EVM execution. So Polygon released one on a rollup, and Scroll also had one. And since then, there have been a few others. I would say in the last 2 years, we've seen a rise of just more generic general purpose zkVMs. So there are quite a few in the market today. I think RISC-0 probably was the pioneer here to choose the RISC-V architecture. And there's also SP1, Jolt, and a few others. And so, yeah, we came into this landscape while thinking about the origins of OpenVM. And what we found is that all of the existing zkVMs are pretty opinionated about the instruction set that developers are going to use to express their code. So obviously with Cairo, you have some custom instruction set that is pretty strange from a standard developer perspective, but it's very efficient in zk. With the zk EVMs, you have EVM, which obviously developers are quite familiar with. And the challenge there is that EVM is extremely complex and actually quite difficult to express in zk. And then, of course, with the RISC-V focused VMs, RISC-V is a very generic instruction set. And so it's possible to emulate many different other types of instruction sets on top of it. So for example, I think both RISC-0 and SP1 are pretty focused on emulating EVM through running REVM or even REF on top of RISC-V. So at OpenVM, we're taking a slightly different approach, which is to not be as opinionated about the specific ISA that developers are going to be targeting. And what we realized is that the constraints of zk actually don't force you to really commit to an ISA in your zkVM framework. Obviously, in the normal computing world, you have a physical processor that has some ISA, so you don't get that much flexibility. But we realized it's possible in zk to really relax this restriction. And as a result, we've built OpenVM to be quite modular in terms of the ISA. So to give a sense of what that means, we have full RISC-V support through what we call a VM extension. That's a set of opcodes that are supported in the OpenVM framework. But developers can also use OpenVM to construct a totally different zkVM that's focused on proof aggregation. And so our framework allows developers to mix and match existing opcodes, as well as define their own opcodes that will all interoperate on a shared set of memory spaces.
Uh, okay, quick question. Is someone building the EVM on top of this?
Um, not yet. We would love to see a team come in and try to do that. We do have the standard emulated EVM support by running REVM or RETH on top of OpenVM. Um, so today we're already able to prove Ethereum mainnet block execution with verification in an efficient on-chain manner.
Awesome. Why is it that complicated to express the EVM in terms of circuits?
Yeah, I would say it's maybe just because of the intrinsic complexity of the EVM. If you try to compare the EVM and RISC-V as an instruction set, you'll quickly notice the EVM has way more instructions. And also the EVM has native 256-bit words. And that's a bit strange from just any computing context. But in ZK, it's challenging because that's a very large word size relative to the basic building blocks of ZK, which are these sort of prime field elements. And so that just has an intrinsic performance overhead.
Okay. Okay. Yeah, maybe let's jump into the modularity. I'm looking at the README right now, and the first thing is modular no CPU architecture, which is very interesting. Like, why the decision to not include a CPU
Yeah,
architecture.
so it's obviously pretty weird to have a VM that doesn't have a CPU. And this is
Mm.
what led us to believe that having a modular zkVM design was even possible from the ground up. So to explain what our no CPU design even is, most zkVM designs that we're aware of have a central part of the ultimate zk circuit that emulates a traditional CPU. So what a traditional CPU does is at every clock cycle, load the instruction from the program that should be processed and delegate the execution of that to different other components of the processor. So if you look into the design of all traditional zkVMs, there is just a zk circuit that enforces that functionality. Now, in a physical processor, you must have a CPU just because there's some physical unit that is processing all the instructions. But actually, the computational constraints of ZK are a little bit different. And it's possible to somehow virtually emulate the behavior of this CPU without having to materialize it in a ZK circuit. So the details are a little bit complicated, depends a little bit on the use of randomness in the ZK circuit design. But the conclusion is that in our no CPU design, there is no CPU circuit. And actually, what we have is for each group of opcodes, some circuits that enforce the behavior of just those opcodes. And they communicate with all other opcodes through some randomness. And what that specifically means is that if you want to add an opcode to the system, you don't need to let the rest of the system know about it. It's kind of like the execution is being delegated between different chips that are floating around the system, but the coordination is somehow enforced by the underlying ZK argument without having a central coordinator. So this is sort of the core design choice we make that really enables the modularity throughout the rest of the code base.
How's the performance of this?
Yeah, so today or in late December with our first release, we feel like benchmarking on mainnet block execution is kind of a reasonable benchmark. We got to sub-cent per transaction proving costs in December, and since then we've been working pretty hard on just performance optimization. I think we're at about 3x better today, and we'll cut a release in the next couple weeks where we hope to have some even more significant improvements. Now, I will say performance is a little hard to compare between different VM architectures, just because obviously every VM is trying to improve on benchmarks and also probably cherry picking some benchmarks that are good for them. So yeah, like a big factor is hardware acceleration. That's a topic we're working on actively, and I think it'll be more interesting to compare once we actually have that hooked in.
How do you internally test it? So, okay, you said on transactions on Ethereum. Yeah, well, what else? Like, what benchmarks do you normally use to test this stuff?
Yeah. So we think of this in terms of micro benchmarks and sort of integration test benchmarks. For integration, just a really big, diverse workload, we do think pretty randomly selected Ethereum mainnet blocks are a good workload. That's what a lot of the industry is interested in. And it's pretty heterogeneous in terms of compute. Like you need to do some hashing, you need to do some elliptic curve operations, and then you need to do a lot of memory access and iteration. So there we're targeting some pretty recent blocks. We like to choose the block 21 million for mimetic reasons, but that's just randomly chosen. Uh,
Nice.
yeah. Outside of that, on micro benchmarks, we do like to stress test the system on different workloads that encompass each aspect. So our system supports using the modularity, VM extensions for elliptic curves, for hashing, and also for big integer arithmetic. So things like int 256. And so we have some benchmarks using REVM with heavy usage of EC recover and EC pairing to test the elliptic curve support. We have some hashing. I mean, EC recover also already has some hashing. And then on the memory access and just looping support, we developed a regex benchmark using some of the code from zkEmail, which we find to be pretty memory intense and relatively good way to measure progress. Ultimately, like we do feel it's important to take real world workloads. That's why we think the Ethereum mainnet block is probably the most indicative. But when you're developing, it is helpful to have micro benchmarks that isolate different components of your system performance, so you can understand whether a change you made is actually driving improvement in those components.
Okay. Let's say, okay, I'm someone who's interested in a zkVM and I want to use the OpenVM for that. Like, what would be the steps necessary to, have a working thing in the end?
Yeah. So you can write a program just in Rust through our Rust front end.
Mm.
If you're just writing vanilla Rust, it should work kind of out of the box. There are some caveats, like of course you can't use system level features that are not provable in zk, but those caveats are really from just properties of zk.
Mm.
Now, if you want additional features and to accelerate some special purpose operations, we have support for acceleration for ECDSA, pairings on BN254 and BLS 1231. We also support SecP256R1 for the P256 curve common to secure enclaves. On hashing, we have support for Ketchak and SHA-2, and then we also have support for modular arithmetic. So for all programs involving that, you can simply import some libraries that we've written that modify pretty popular existing libraries for those components. And in the OpenVM stack, you'll see directly the increased proving performance. We also support proving unbounded length programs through continuations. So what that means is that if you write a very long execution, we will divide it up into pieces and do the proof aggregation to allow you to get a final proof that is verifiable on chain in the EVM. I think the verification cost should be around 300,000 gas.
Okay, why is the proof aggregation faster than just doing the whole thing?
Yeah, it typically does add a little bit of overhead since obviously you're doing proof
Mm.
recursion, whereas if you just did the whole thing at once, you wouldn't. But the challenge is that there are some workloads where the circuit size is just too large to fit in a single proof. So we're using the Fry proof system using Plonky 3. And from the theoretical foundations there is a maximum size of what can be handled. And outside of the theory, there's just a practical constraint that any given computer will have a maximum size that can be proved. And so
Okay,
what
just
continuation? Yeah,
just
good.
because you're running out of RAM. That's the constraint.
Yeah, there's really two constraints. Probably
Okay.
the RAM will hit first on most reasonable computers, but even on the best computer in the world, you'll have a constraint just from the theory. So the proof system is only going to
Mm.
work for a circuit of some pretty large size, but still it's bounded.
Okay, interesting. And that's why you're doing the aggregation. Okay, to summarize, basically, okay, there is a Rust front end. You can write your typical Rust stuff with some restrictions, things that you cannot prove in ZK. That gets compiled to RISC-V, right? and then you're doing your proof stuff on RISC-V opcodes or whatever.
Yes, so this is actually a place where our design is a little different from the RISC-V oriented VMs,
Mm.
where we do use just the standard Rust compiler to compile to RISC-V. And then we have an additional step where we transpile RISC-V into our more ZK native instruction format.
Mm.
And so for RISC-V instructions, the behavior is exactly the same. So the transpilation is a very thin wrapper. You can see even in the code, it's just line by line instruction translation. But
Mm.
we enable additional opcodes that aren't related to RISC-V to interoperate with the RISC-V memory and the existing RISC-V instructions. In addition, for operations like aggregation, we have opcodes that can write and read to just totally different address spaces in memory, whose formatting isn't the same as the RISC-V address space. So just to give a sense of what that can enable, in RISC-V, the address spaces are on 32-bit words or 4 bytes, and typically in ZK, each field element is representing a single byte. In the what we call the native address space, we allow the memory to be the full field element. So we're using the baby bear field, which is a 31-bit field. And so the fundamental underlying memory structure is a little different.
Okay, so you're transpiling into a custom instruction set that you guys have written.
Yeah, exactly. And you can view this as kind of a pretty large and customizable superset of RISC-V.
Mm. So superset of RISC-V with some additional opcodes to handle some specific things.
Yeah, and it turns out actually the Rust compiler, we found out, has pretty native support for this concept. So
Mm.
there's sort of two types of concepts. So first is something called intrinsics. So I think any developer that's tried to optimize at the very lowest levels of the CPU will probably be familiar with this. So in more traditional programming languages, an intrinsic is just some new operation that's enabled by your CPU that still reads and writes to the same memory space you're using. Often this will be implemented by, for example, Intel for, SIMD optimizations on to do large numbers of arithmetic operations in parallel.
Okay.
So we
SIMD is
leverage
single instruction, multiple data, right?
exactly.
Just for people that don't know. Okay.
Um, and so we kind of use this same support to define custom intrinsics that fit within the RISC-V instruction formats, but are implemented very differently on the back end. And so this is how we support things like catch-ack or ECDSA. Um, Separately, there's an additional concept in Rust and most programming languages, which is called a kernel. So this is more similar to GPU support. So when you try to call a GPU from Rust, there's just some special handling within Rust where it understands that you're delegating from your CPU to some completely different computer architecture, namely your GPU. And it expects that the results, the CPU will delegate to the GPU will do some computation, and eventually the CPU will get the result back. So we use this format to perform delegation from the more RISC-V oriented address space to the native address space where we're free to do operations like aggregation much more efficient.
Okay, let's tie this together with Axiom, right? So basically, Axiom is building, or is Axiom the only team that is building OpenVM, or are there other teams as well?
Yeah, we've been collaborating with the Scroll team as well as some
Oh, okay.
individual collaborators, including
Yeah.
Max Gillett, who was one of the original authors of Alita.
Mm.
And to maybe give a sense of how we got involved in OpenVM at all, the origin was really early last year. We had just released our coprocessor product, and when we were talking to developers about it, we found that frequently we were very close to what they wanted, but they wanted some very small modifications from
Mm.
from the smart contract perspective, modifications that would be very easy to make. But unfortunately, in the architecture of our coprocessor, we were using a circuit-based approach, and it simply wasn't flexible enough to make these small modifications. And so as developers, this was pretty frustrating for us. Like we felt like we were almost there, but we just needed additional customizations. And so we set out to really explore what was possible with zkVMs. And when we sort of evaluated the landscape, we did find that as ZK developers, we needed a little bit of additional flexibility to make sure that we could deliver on all the features we wanted. And yeah, we kind of evaluated using some existing zkVMs, felt a little bit limited and worried about the vendor lock-in. And so we decided to build OpenVM and kind of a different first technical foundation, but also different development model. So you might notice OpenVM is released under a new GitHub org, which is really intended to just represent the open source project. And we deliberately have been working with collaborators from different organizations. And the goal there is to really provide developers a future-proof pathway to use a zkVM. I think one big concern of any developer adopting any ZK tool, but particularly a zkVM, is just vendor lock-in. If the team developing the VM makes a decision that's, bad for your product, or even if it's just strictly good, but it's a breaking change, it's pretty challenging for you. You don't really have much recourse. And as the systems trend a little bit to vertical integration, you're probably going to have less recourse in the future. So our hope for and vision for OpenVM is to grow the contributor set and to have multiple independent teams developing different aspects of the system. And we feel like that will actually give the best future-proofing guarantee for developers and also lead to a more competitive dynamic where there are different proof system backends for OpenVM. And we feel like developers should choose the one that offers the best performance.
Mm. Interesting, interesting backstory. Uh, so where is OpenVM now? In terms of can I use this? Can I play around? What's the future looking like? Yeah, where are we today?
Yeah. So with our initial release last December is the first version where we felt developers can play around and just try out the interface, really generate some proofs. It's currently definitely not production ready, so we wouldn't recommend anyone use it in a security critical context. So we're pretty actively developing it to get to a first production ready release. So there's two main components. First, some just low hanging fruit performance optimizations, and second, getting everything buttoned up for a more formal security review. You'll see some more news from us on that quite soon. We're going to have a security contest. And so we're pretty excited for the community, both to just check out our security, but also learn a little bit more about the underlying architecture and design.
Interesting. Well, yeah, good luck with that, man. I think it's a valuable, I think it's a great name as well, OpenVM. I'm surprised this wasn't taken. It's a good name.
We definitely caught a little bit of flack on Twitter for the parallel to OpenAI, but yeah,
Really?
yeah.
Really?
But
Okay,
it really is the
that's
spirit
funny.
in which we think the project should live on. Like we're pretty inspired by what LLVM has done, where LLVM itself is just a collection of modular tools, but there are many different projects that have adopted those tools to build pretty state-of-the-art systems in different areas. And so in the ZK space, we see today things are pretty hyper-optimized for proving blockchain execution, whether it's Ethereum mainnet or rollups. But we envision actually that as the space grows, there will be different workloads, and those will demand slightly different architectures. And so we think having a more flexible framework is kind of the best way to both grow the space and ensure that developers aren't kind of very narrowly focused on the most popular workload today.
Awesome. Well, yeah, good luck you with the auditing stuff like that. Is there a timeline?
There is some rough timeline, but our focus actually is always that we don't think that it's good to set super strict timelines on security work. So yeah, we although we have some targets, we don't want to publicly commit just to
Fair enough.
obviously we could commit, and if it's not ready, we won't ship it. But we really strongly believe that for security, you have to take a it's ready when it's ready mindset, no matter how unfortunate that might feel.
Fair enough. Fair enough. Listen, Yi, thank you very much, man. It's always a pleasure to have you on the podcast. I'm gonna put the GitHub in the description down below. Any other resources? Is it like a documentation page? OpenVM.dev, actually. Okay.
Yeah, we have a developer book at openvm.dev. And then also for anyone curious about the core architecture, the GitHub has links to some reasonably extensive contributor docs that explain both the theoretical architecture as well as how that relates at the code level.
Fantastic. I'm gonna link all the resources in the description down below. Yi, thank you very much.
Awesome. Thanks for having me on again.
For sure. Thanks, guys, for tuning in, and see you in the next one. Bye.
Awesome.